Now let's introduce the idea of expected values, means, and variances. Okay, what's the expected value? I expect that this might be a new concept for a lot of you. The expected value, or expectation, or mean. So let me just be clear here. We often will say expectation. This isn't exactly correct. We should always really say expected value, but I will slip up. You'll find other people in the field slip up as well. So just for the sake of this course, when we say expectation, we're meaning expected value. An expected value is really a mean or an average. For any random variable y, the expected value is denoted e of y. This thing here, let me grab my pen, this here, the expected value of y. So this e means the expected value. It's the long run average of the value of the random variable. The expected value of a discrete random variable is the weighted average of the possible outcomes of that variable, with normal weights equal to 1. The notation is the expected value of y is equal to mu y. This little term here is mu y. This is the population mean. So this means that if we were able to take the average of the entire population, the expected value is what we would get. Some formulas. Okay. For a discrete random variable, the formula for the expected value of the random variable y, which can take on k possible values y1 through yk, each with probability p1 through pk, is the expected value of y equals mu y. So I'm just going to write this bit again because it's by definition. We'll see mu y a bunch, and it's equal to y1 times its probability plus y2 times its probability plus, and so forth, yk times its probability. And then because we're summing, we're going to take this sum and we'll represent it with this sort of funny E looking thing, which is the sum symbol in math. And this just means we're going to sum from I equals 1 to k of yi and pi. So we're indexing y, the outcomes, by I, and the probabilities by I. For a continuous random variable, the formula of the expected value is going to be slightly different. We're going to y can take on a continuum of values between negative infinity and positive infinity, so the probability is going to be written as probability that y is in between negative infinity and, or greater than negative infinity and less than positive infinity, with some probability distribution function fy of y. The expected value is going to be the integral. I should have the negative on the bottom of that integral, sorry. So then this negative should go down here. The integral of this PDF multiplied by each value y. Let's do some examples of a discrete random variable expected value. So I might write expected value as EV. Okay, let's say we have a random variable that's a gamble of $110 with a probability of 99% and $0 with a probability of 1%. We could say if our random variable is y, this is y1, this is p1, this is y2, and this would be p2. And so we are just going y1 times its probability and y2 times its probability. And so we can just do that with a little algebra, and we get $108.09. So the expected value of this gamble is $108.09. A Bernoulli expected value. All right, so a Bernoulli random variable. Let's say we have f takes on two values. Takes on the value 1 with probability p, and 0 with probability 1 minus p. So then we're taking the first possible outcome 1 times its probability here, plus the second outcome times its probability, and so the expected value of a Bernoulli random variable is just p. Some properties of expectations. See, I did it here. This should say expected values. Suppose k and c are constants and x1 and x2 are random variables. So what's the expected value of what's the expected value of a constant k? So this is essentially asking what's the expected value of, suppose, the number 3. 3 is not a random variable, so if what's the average of 3? No matter what we do, it's just going to be 3. What's the expected value of a random variable plus a different random variable? We can distribute this expected value through, and we can get expected value of the first plus the expected value of the second. What's the expected number 3? What's the expected value of a constant times a random variable? The nice thing here is we can just take this constant out. Number 4, let's put some of these together. What's the expected value of a constant times a random variable plus another constant? Well, we're going to use each of these properties, and we'll get what's left here. So that we can distribute this expected value through. We could write this out a little bit bigger or a little bit more explicitly and say this is equal to the expected value of k times x plus the expected value of c. And then we know that the expected value of c is just c. And then the expected value of k times x, we can use this property, and we get k, expected value of x. A couple things to note. Numbers 5 and 6, the expected value of the ratio of two random variables is not equal to the expected value of one random variable over the expected value of the second. And then likewise, we can't distribute the expected value when the two random variables are multiplied. That's number 6 there. Let's do another example. Find the expected value of a roll of a die. So let's define the roll of a die. So x is going to be the random variable roll of a die. Now what values does it take on? So x1, x2, x3, x4, x5, and x6. We're going to assume this is a 6-sided die. Takes on the value 1, 2, 3, 4, 5, 6 with probabilities P1, P2, P3, P4, P5, and P6. All of them are probability 1/6. Okay, now what's our expected value formula? The expected value of x is equal to the sum of I equals 1 to 6. Why do I know 6? Because there's 6 possible outcomes of y. We're dealing with x, not y. So of yi times each probability. So we can expand this sum to make it a little more explicit. Let's do that. It's going to be y1 p1 plus y2 p2 plus y3 p3 plus y4 p4 plus y5 p5 plus, doesn't let me write off the side of this, y6 p6. Okay, so really what we're doing here is just taking the average of a roll of a die, but we're writing it out in math form. Alright, now we can take all the values over to, shoot, I did it as y's again. I should have written those as x's, I'm sorry. Now we can take all these values over here and plug them into our formula. So then we would get 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. All right, and if we just do this math, we get 3.5. So the expected value of a roll of a die is 3.5. So that's how you use this formula. All right, higher order moments. We're going to talk about the standard deviation and the variance, which are measures of the spread of the probability distribution. So the variance, what is the variance? The expected value of the square of the deviation of y from its mean. And so this is, the variance is essentially, okay, if we have two distributions, one that looks like that, one that looks like this, the variance of the first is going to be larger than the variance of the second. We're really kind of getting a measure of how wide this thing is. The formula, well, first things, so remember, expected value of y we write as mu y. Variance we write as sigma squared y. So this term here is sigma, and then of course it's squared, and then we're denoting which random variable we're defining over, so it's y. So sigma squared y is the variance of y, and here's the formula. It's the expected value of y minus its mean. So we could write this as expected value of y minus mu y squared. For a discrete random variable, the formula is here. It's the sum of I equals 1 to k of yi minus its mean squared times every associated probability. Just a quick note, normally we think of the standard deviation because the variance is in squared units, and the standard deviation is going to be written sigma y, which is equal to the square root of sigma squared y. Alright, let's do an example. Suppose the number of computer crashes in a year is a random variable y, so y1 is equal to 0, y2 is equal to 1, y3, oops, I should have 3, 4, and 5 crashes there. The probability of each, so the probability of 1 is 80%, the probability of 0 crashes, p1 is equal to 80%. The probability of 2 crashes, y2 is equal to 10%, 3 crashes, 6%, etc. So let's look at how we do this. Expected value and variance calculation. So we know how to calculate the expected value. We just did this for a roll of a die. We can do it for these computer crashes as well. So we're going to write out the expected value formula. It's equal to the sum of I equals 1 to 5, because we have 5 possible outcomes, of yi times each probability pi. And then we just plug in the values from up here. And we get 0 times 0.8, plus 1 times 0.1, plus 2 times 0.6, plus 3 times, this should be 0.06, plus 3 times 0.03, plus 4 times 0.04, which is equal to 0.35 crashes. So the expected value is, for every year, you're going to get 0.35 crashes per year. What's the variance of this thing? Well, let's plug in these values for this for this formula. Here's the variance formula again. We can expand this if we want. So really what we're doing is going to be, for every I, we'll have, let's just do the first couple, y1 minus mu y squared times p1 plus y2 minus mu y squared times p2. And then we would go all the way out to 5, because there's 5 possible outcomes. And then we would plug in the values. So 0.35 crashes is mu y. That's what we're doing here. We're plugging in 0.35 crashes. We're plugging in each value of y into their associated places. So we're going to have 0 minus 0.35 squared times its probability, which is 0.8. And then we'll plug in 1 minus 0.35, that's this part here, y2 minus its mean squared times the probability of 0.1. Plugging in all those values, and we get a variance of 0.6475, standard deviation of 0.8. Let's do some properties of variances. Okay, so the variance of a constant is equal to k. In other words, the variance of the number 3 is equal to 0. There's no variance. Variance of a random variable plus a constant is just the variance of that random variable, because the variance of the constant is 0. Variance of the sum of 2 random variables is equal to the variance of the first plus the variance of the second plus 2 times the covariance. I know we haven't defined the covariance yet, but this is what it's equal to, 2 times the covariance of x1 and x2. The variance of the difference of 2, number 4, is the variance of the sum of each independently minus 2 times the covariance. So the only difference is the minus sign here. This one's important, number 5, the variance of a constant times a random variable. We're going to pull that constant out, and we're going to square it. Why? Because the variance operator is a squared operator. go back up here. Notice the squared term. Anything that comes out of that variance is going to be squared. And so we can put these together again, and then we can take for number 6, we can do the variance of a constant times a random variable plus a constant. So let's take number 2. Number 2, that's going to be the variance of the random variable plus a constant. So the constant goes away. So then we're just left with the variance of the constant times the random variable, and then we'll use number 5 to take the constant out, and we'll square it. And then number 7 is just putting a bunch of these together. All right, let's do an example. An example of how to manipulate expected values, or to use expected values. So I want to show that sigma squared, the variance of x, is equal to the expected value of x minus mu squared, or expected. I want to show that these two things are the same. You're going to be asked to do this on your homework, by the way. Okay, so let's start with the left-hand side over here. Now let's just expand the square. So taking x minus its mean squared, we get x squared minus 2x times mu plus mu squared. Then we'll distribute the expected value through. So then we can take this expected value, distribute it through. Because these are sums, we can do that. We'll get expected value of x squared minus 2 times the expected value of x times the expected value of mu plus expected value of mu squared. And then we get the expected value of x squared. We can't really do much with that, so that stays the same. Minus 2 times the expected value of, or 2 times mu. Why? Because by definition, expected value of x is equal to mu of x. So then we get 2 times mu, mu times mu plus expected value of mu squared. Now we're just simplifying this bit, so then we get minus 2 mu squared plus the expected value of mu squared. I should note that mu squared is a constant, and that's why this part drops out here, so we're left with mu squared, or the expected value drops out. Why is mu a constant? Because we're taking the mean of a population. The population by definition doesn't change, and so the mean of the population is a constant. And then we can subtract these two or add these two, and we get what we were looking for, the second half of this equation here. Let's find the variance of a Bernoulli random variable, another example. Alright, suppose we have a Bernoulli random variable. It's defined as x. It takes on two possible values, 0 and 1. The formula for it is, by definition, we're going to write it as sigma squared x is equal to the variance of x. The formula for it is expected value of x minus its mean squared. And then that's the sum of I equals 1 to k of xi minus its mean squared times each probability. Then we're just going to expand it because we know we have two possible values. Let's write out our Bernoulli random variable real quick. x1 with probability p1 and x2 with probability p2. Usually x1 is going to be 1, x2 will be 0. And this will be p, and this will be 1 minus p. Okay, so in order to find the variance, we need to know mu of x, right? That's the first thing that we need to figure out. So we need to know mu of x. Let's figure it out. The expected value of x is equal to 0 and 1, so we're going to sum over x equal to 0 and 1 of xi pi. We're going to expand that sum, so then we get x1 p1 plus x2 p2. Let's plug in the values. x1 is just equal to 1, x2 is equal to 0, so that's what we get here and here. And then we'll plug in the probabilities. P1 is equal to p, p2 is 1 minus p, and that simplifies to just p. So the expected value of x, or mu of x, when x is a Bernoulli random variable, is just p. All right. So we can take this information and plug it back into the variance formula. So the variance of x is going to be plugging this back into this formula up here. I'm going to plug in the values, and we get 0 minus p squared times 1 minus p. So this is going to be mu of x, and 1 minus p squared is mu of x. This is going to be p2, and this is going to be p1. We'll simplify this whole thing with some algebra, and we're ultimately left with p times 1 minus p. So the variance of x, or sigma squared x, when x is a Bernoulli random variable, is p times 1 minus p.